All right, and we're going to just start from here. This is the flow chart that I want you having in your head, okay? And so you have matter. This is most things that you encounter in your life, they're going to be matter, okay? The only thing you regularly encounter that can be considered not matter would be things like information is actually typically matter, in case you're wondering, because it actually has weight, if you're ever curious. But things like energy would not be matter, okay? So energy would be the form of substance that you encounter that is not matter, okay? That is what you encounter that is not matter. This can include things like electromagnetic radiation. Can be considered not matter sometimes. It kind of depends on what classification you do. But in general, energy is going to be it. So matter, this is going to be broken between pure substances and mixtures. So we need to classify that into smaller amounts, because if we just classified it as a study of matter and everything was matter all the time, then that'd be basically everything you encounter in every day, right? And so, congratulations, everything you do all the time is chemistry. All right, and so pure substances would be further broken down. We have the elements, and these are going to be one thing that has consistent properties for that entire thing, okay? And these are going to be the smallest possible increment you can get in them. So this is your element. Then we have water molecules, which are going to be compounds, right? And so these are two or more elements together, okay? They're going to make up compounds. Compound meaning compound, as in conjoining the two things together, right? Two or more things, okay? As in compound interest, as in compound anything, right? And then so right here we have mixtures, and these are going to be further divided between homogeneous and heterogeneous. Homogeneous meaning I can't clearly delineate any specific portion of this as being different. Heterogeneous, I can visibly delineate differences between them. Okay? What would a salad be? Nice salad with some dressing and tomatoes and carrots and all that. Be a heterogeneous mixture, right? Okay? Soda pop, not with bubbles. Homogeneous. Okay, so these elements we've been talking about, well, we have broken those into the periodic table and sorted them into that periodic table. You see one up there. And this is a listing of all the elements that we found. It doesn't actually necessarily have to be on Earth, but we have found all of these on Earth. If we found them, we put them on there. The periodic table consists of many small blocks. Those blocks actually holds different elements in it. Each of the letter or two at its center, you will notice if you ever see one with 3 letters, that means it has not been given an official name yet. Okay? So if you were to look at an old periodic table, this one's fairly new, as far as I say. Yes, it's new. There was like a 10-year period where the committee that names these things got into this big fight and refused to see each other. And so finally a few of them died and they started seeing each other again. This was about a decade ago that they started seeing each other again. And so if you have a periodic table from before then, this entire bottom row, half this bottom row was 3 letters. And that's because they didn't have official names yet. Okay? And so that committee used to be very childish. But the sad part is that isn't even uncommon for scientists. Like, yeah, we get into fights. Some crazy stuff happens. Like the Brontosaurus. So, you have the letters. These are going to be the chemical symbols. They'll represent the name of each element, though not always in the way that you'd expect. So the majority of them are going to be some combination that makes sense for that name in English, okay? But when this periodic table first was discovered, when it first was started to being assembled, the academics of the day all spoke Latin and Greek, okay? That was something that if you were going to be a scientist or an academic, you weren't taken seriously if you didn't speak Latin and some Greek. Okay? And so a lot of these things are going to be named in such a way that they're going to be in a Latin or Greek. And a few of them are done in just kind of some. They couldn't figure out a letter combination that made sense. And so they did mythology, basically. Okay? There's a cuprous, copper, Cu cuprous, that has it having to do with the mythological entity of German descent. I believe iron is as well, ferrous. So it's a like god from old mythologies. Okay. But you have things like, for example, lead, which is PB up there. See PB on the bottom right, 82. Okay. You probably know like plumbing, right? You've heard of plumbing. Okay. Hopefully. Not. Oh my goodness. Plumbing comes from lead pipes, and it's plumbous, and that's the name for lead back in the Latin days. Okay, and so they used that for lead, right? Gold is like that, and so is silver. That is the AU and AG. Argenta, you may have heard of Argenta, especially in like sayings. Blood or silver. If you ever heard that saying, that uses Argenta in it. Okay, so anyways, aurum is gold in case you're wondering. For example, sodium is Na up there. It's near the top left. That is natrium, which is the Latin. Okay. So this right here, again, is the periodic table just put up here. You'll notice that has colorings on it. If they can be colored. There's a little black line right here that zigzags like that. Everybody sees that okay? This portion right here, this is actually one of the shames about not having physical textbooks anymore, the paper textbooks, is every physical chemistry textbook used to have an actual periodic table in it. So the actual periodic table is not that formatting, that shape. The actual periodic table, this inserts right here, and so the periodic table actually folds out with this in the middle here. Okay? And so it should be like this long thing about that size if it was textbook size. Okay? And in old textbooks, you actually could pull it out. It would actually like unfold and it would change so this was up under it where it should be. Okay, and then you could fold it back and it looked like this. Yeah. It was actually kind of nice. No longer can do that though. It's digital. You can, however, look up the properly formatted periodic tables with that inserted in. They are online. Okay. It does not show up well enough for you to be able to read it on this projector. So I don't bother anymore. This right here then, you'll notice these right here are all the same coloring. And that's because these are all metals. Okay. This right over here, these are called the metalloids, and these right here are the nonmetals, right? Some of these have these colored in such a way that they would be the state of matter it's in, right? Gas, liquid, salt, okay? This one has it colored in such a way that's the state of matter. So you'll see the red ones there. Those typically are going to be gases. The bromide, mercury, those are liquids at room temperature. And then the rest of that, the black there, is the salts. Okay, in case you're wondering. These, see the periodic table up there, how some of them are not filled in. You don't see any, like, their outlines of the names. NP on the bottom. Okay. That means that we only have encountered them as man-made elements. We have never encountered them in nature. Okay? So you'll see that everything after basically your rank here is man-made. Right? And then there's this one right here, which is just incredibly rare in nature, if it exists in nature. It probably just falls apart immediately if it ever gets made. Now, some of the elements that we've found in nature like francium, have only ever existed for half a second. Okay? So we like, oh, francium's there. Boom. No, it's not. Okay. So don't get me wrong, everything past lead is radioactive, and some of them get really radioactive. But and so they are self-destroying. But those ones that you saw that are outlines only, we have not actually encountered them in nature yet. Okay. It would take some really extreme conditions to actually ever encounter them. So on Earth, probably never going to see them. Okay. Unless you're in a collider or something. All right. Now, when you look at the periodic table, those vertical groups, see how they have numbers at the top? Okay. Those right there are called groups. Each group is going to have a number and a letter associated with it. This one right here just has numbers on it, but this is a bit more of a typical periodic table, which has both types of numberings. Okay. So what you'll see is you can number it 1 through 18. You'll see and catch me saying group 1 and then calling like boron group 3. And that's because those are the A and B groups. Okay? So if we just did them as groups with 1A, 2A, 3A, we skip these 10 down here. Okay? So the group numbers on that periodic table up there, 13 would be 3A. 14 would be 4A. Okay? And these are called the main group elements. And the reason that people do that is if you get to right here, this is 99% of the mass of the solar system. Okay? It's the vast majority of the mass of the solar system. In fact, if you just get to here, you're already looking at the majority of the solar system. And in fact, just going to here, you're still looking at the majority of the way of the solar system. Because the sun. The sun weighs more than all the planets combined. And so these are the main group elements right here, and that's why they're given a special designation, and oftentimes they're going to be the only thing you actually need to talk about. Okay? If we're being realistic in terms of like biology and sort of the biochemical sciences, you actually pretty rarely see this other stuff. They're minor trace elements in your diet. They're minor trace elements in your body. Okay? You do need quite a few things. For example, iodine, you need that for your thyroid. It's the only place it's found. Iron, though, is in your blood, for example. Copper is actually necessary. Anybody know you need copper in your diet? Yeah. A lot of people don't realize, but yeah. I know, right? But if you look here, by far and away, phosphate is a much, much, much heavier present substance in your body than any of those. In fact, all of the rest of that combined. And then you go up to carbon, oxygen, nitrogen, and that's the majority of your body other than the hydrogen, which is also in the water in your body. Okay? So water being H2O, right? So that's already like the most important elements right there. You can almost skip these in terms of just pure mass, right? So most situations you actually can get away with just using main group elements. Okay? And so that's the 1 through 8A. Transition elements, once we include those are going to be the designations for B right here. So for example, 3B, 4B, 5B, these are transition elements. Okay? And the last thing is these Roman numerals that you can see. Nope, I don't have Roman numerals on this one. You can actually find periodic tables with Roman numerals, in which case those are still the transition elements, just another way of representing those. You'll note that these are actually gathered up. For example, this is 8B right there, right? Can you see that? It's called the Calic triad. They react very similarly. Okay? And so you'll see if you ever find one with the Roman numerals, they'll also have like that, where it has some of them grouped up as similar reactivities. Kind of depends on what you want to try and use for So the system that's used by IUPAC, which is the one that sets the standards, so that's the International Union of Pure and Applied Chemistry. Again, these people are kind of crazy. So keep that in mind. My advisor used to swear them out all the time and refuse to use certain things that they put in. But he could do that. He was old enough. I can't do that. So this one is 1 through 18. They have said that the official way to do the periodic table is 1 through 18. That is the proper way. That is what's on that periodic table. You'll still find the other ways done many, many, many different places. A lot of people don't necessarily follow IUPAC's guidelines completely. Okay? But that's what it is. They get into fights quite often, by the way, and don't meet for like one time, almost 2 decades. So, yeah. The horizontal row, this can be known as a period. And so you guys are familiar with periods or repeated patterns, right? And so this is repeated patterns that we're going to see. Okay? And so when we look at groups, they're going to actually have the same sort of properties. So for example, BE and MG on that second group there, they react fairly similarly. They have very similar properties. Okay? And again, the periods are going to be numbered 1 through 7. You'll notice that periods 6 and 7 are actually on the bottom of the periodic table there. Okay? And those are where the thing on the very bottom is called the lanthanide series. That's where those insert. That's why they don't have their own like numbers. They go into periods 6 and 7. Okay? We don't currently have anything past period 7, but maybe they'll make something. Okay? That'd be interesting. They'd make all the periodic tables have to shrink, right? All right. So the staircase-shaped line, which I had mentioned before, that's that zigzag darker line. It's not on that periodic table, apparently, which is weird. This right here. Everybody see it okay? Yeah. That right there is where you would find the metalloids. Okay, that's where you're going to separate the metals and the nonmetals. Okay, it's going to begin at boron, and the elements that are bordered by the line, with the exception most time periods of aluminum, these are going to be called the metalloids. Okay, they're the ones that are typically going to have 2 sides that would touch that line, and so they're these things right here. See those? They're the green things. The metalloids are going to be kind of like metals, kind of not like metals. Okay? They're going to have properties that are a bit like both. Okay? You'll notice silicon, the semiconductor, i.e. the thing that makes computer chips, is typically considered a metalloid. Okay? Kind of has some metal properties, kind of doesn't. All right? Aluminum sometimes is joined as a metalloid. Boron is sometimes in that group. As of this book's publication, it was part of that group. But they get argued and end up getting dropped and added every like 10 years or so. Okay? And so it kind of comes out down to like what the most recent testing and definition ends up being, whether they're going to be a metalloid or on their side. Yeah. Aluminum would end up being a metal, and it's considered a metal for this publication, and for your testing purposes, metal. Okay? Boron is considered a metalloid as of this publication of this book, and so that will be what you'll on the tests and such. Okay? But it actually does get dropped into the nonmetals sometimes. Every like 5-10 years, there's an argument. So, whatever. Somebody comes up with a new way of testing, and it ends up being not in there. Or in there, one of the two. So there's several elements that are going to be essential for human health and in general life in general, though there are some differences depending on species. Those needed in the largest quantity that makes up the vast majority of your body are going to be carbon, hydrogen, oxygen, nitrogen. They're going to make up the vast majority of biological molecules. By far and away, They're what you need the most in your diet. And so you'll notice that that's what composes the vast majority of your diet, right? Macronutrients, macro meaning larger amount, is going to be the quantities that you need 100 milligrams per day or of. And they're going to be things like sodium, magnesium, potassium, calcium, and chlorine. Okay? And so you need fairly significant quantities of those. 100 milligrams is. Does anybody know how much 100 milligrams is, by the way? Any ideas? Okay. So a gram would be like, I don't even know, how do I describe it? Like a fairly large, like a candy. It'd be the size of like an M&M. Okay. A milligram would be 1,000th of that. And so like this would be less than 1/10 the size of an M&M. Okay. So it's pretty small amounts still, but compared to micronutrients, it's a it's a lot. Okay. Most micronutrients, the cutoff is 100 milligrams per day for macro versus micronutrients. But so you need quantities less than 100 milligrams a day for micronutrients. But a lot of these micronutrients, you can go months without eating any. You can just have none. Okay. They literally fulfill all of your iodine requirements by using iodized salt that has a tiny, tiny amount of iodine in it, like 1% iodine. And so that gives you everything, even if you don't normally put salt on it. Okay? You don't need that much iodine. You recycle almost all of it. So you just don't need a lot of these. And most people get away with almost nothing in their diet for. Though you will suffer over long term if you don't get it. Okay? Everybody knows you don't actually need vitamins. A typical person doesn't need vitamins. Like there's never been a single study that's shown any benefit for taking vitamins. I know, right? Because you mostly only need this stuff. This stuff comes in everything. These things are in almost everything, so you don't need to worry about that. And so the only stuff you really need to worry about is this thing and some of the essentials, which we'll talk about much later. Anyways, those are things like zinc. You need iron in your diet. Fluorine. Anybody think you needed that F up there, fluorine, in your diet? You hear about fluoride all the time, right? You actually need a little bit in your diet. Iodine, of course, and we talked about it with the thyroid. These are where they show up on the periodic table. You'll notice they kind of map to how much there is available in our environment, by the way. So, like this stuff right here is a lot less of our environment. And so they're more difficult to get if you're just like scrounging around, right? And then this stuff, more available, and then this stuff, highly available. All over the place. Okay? Things become less available as you go across and down. Okay? So, a pure substance is going to contain two or more chemically combined elements. This is going to be a compound. Compounds are going to combine elements in specific ratios. And so chemical formulas are going to show that specific ratio. If you have that specific ratio, that is that compound. Okay? So for example, we have water, and that's H2O, right? Everybody's probably heard that before. So if I have H2O, that's water, right? If I have H2O2, is that water? Okay. Anybody know why the chemist went to jail? No? Okay, so me and my friends were hanging out, went into the other room, called back to them. Hey, you guys want some H2O2? They said, yeah, of course I do. And so I gave them a little container of it, and the idiots drank the damn stuff. What the hell? Okay? Not my fault they died, right? Why is that funny? What did I just communicate to you? My friends thought I said you want H2O as well, right? And so they said, sure, I want some water to drink. What is H2O2? It's hydrogen peroxide. So they're given hydrogen peroxide, and then they would have died, right? And of course, that's a joke. Hydrogen peroxide, at least. Oh, that's really messy. I don't want to clean my carpets like that. Okay. So, again, this is going to be 2 hydrogens, 1 particle of oxygen. Those are the atoms that compose this compound. If you have table salt, this would have a ratio of 1 Na to 1 Cl. That's NaCl, and that would be table salt. Okay. If you have that ratio in that same organization, you have table salt. Okay. There's also another deal that you got to realize that, man, this is going to be the first time I say it, and I'm going to end up saying it a lot of times. Okay. Very large organizations that hold way too much power, don't know any science at all, and are really, 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 really stupid. Okay? And so that's something that we just have to accept living in this planet. And it doesn't matter whether you're in the United States, Europe, wherever, it doesn't matter. Okay? That is just a truism, right? And so, there is an organization called Greenpeace. Anybody heard of that before? It's the best funded green organization on the planet. It gets over $10 billion a year worth of funding. They're the ones that usually do those like save the rainforest and recycling drives and all that sort of stuff. They're extremely well funded, almost everywhere you can imagine. Their website, for as long as I've checked, I stopped checking a few years ago. You can check for me, maybe. Said that CO2 that's put out from a car, CO2 that's breathed out by a human being, and CO2 that's put out by a plant or an animal in the rainforest are different. The ones that are put out by a human being or a car is harmful. The ones that are put out by a rainforest or an animal is not harmful. Can anybody tell me what's wrong with that? They're the same. If you have CO2, it's CO2. It doesn't matter where it comes from, right? It's not harmful or helpful or just is, right? It's like saying money has blood on it or something, right? Yeah, the source of money could be bad, and you putting too much of that into there could be bad, but the money is money. Nobody cares or knows the difference. Why all the cocaine, all the $20 bills in the country have cocaine now. Because nobody knows the difference, right? Doesn't matter what that was used before for. Doesn't matter where the CO2 came from. It's the same when it's in the atmosphere, okay? Whether you breathed it out, your car breathed it out, or the plant breathed it out, okay? The fact that a multi-billion-dollar a year organization who sets policy for global warming didn't know that is just a whole nother level of problems. But now you know that, hopefully, okay? The worst part is I had a science student quote that damn website to me on a speech. That's how that came to my attention about 7 years ago now. And I was like, no fucking way. No way. And I went on during the presentation. I'm like literally just made him sit there and looked it up. I'm like, you're right. Jesus. You know why that's wrong, right? The sad part is I had to explain to him, which is so, but now you know. Okay. So your chemical formula, this is going to identify which elements and how many atoms of each element are going to be present in a compound. Now, this is not the end-all, be-all of this tells you absolutely everything about that compound, but it gives you most of that information, okay? And for simple compounds like CO2, it gives you all of it. There's no other structure it could be, okay? There's CO2, that's it. Carbon monoxide, CO, there's nothing else it could be. It's just one thing, okay? But more complex compounds, you may have seen like DL for your different types of proteins and stuff you could take. if you're trying to exercise or different types of supplements that you're going to want to take. We'll get into that actually. That's about mid-semester that we'll start talking about that, but that's the arrangement of the atoms. Okay? Okay, so let's talk about states of matter and how can matter change. Okay? So the first thing I want to get into is a physical change. So this is going to be the change in your state of matter. This is going to represent a physical change that we changed the state of matter. That's one type of state of matter, physical change. So in a physical change, the form of the matter is going to be changed, but the identity will remain the same. So if you start off with water, you're going to have water. Okay? Everybody's aware of the states of matter? Solid, liquid, gas. Any others? Aqueous is actually mixtures. And so that's a liquid water mixed with something else that's dissolved in. Okay? But you are absolutely right. Very often put in as a state of the matter because it's very, very common on this planet. But there actually are some other phases you can be. For example, plasma, like the sun, or a blowtorch, or lightning. That's also another state of matter. Okay, and there's a few others that you can be. But they're really rare, and you don't want to be next to them. So you're never actually going to be next to them. Okay? And interacting directly with them. Ideally, you would. Actually, plasma, you can actually get plasma torches that won't hurt you. So they can actually take off plaque from your teeth and stuff and purify the surface. It's kind of crazy. But so let's say we took a ice cube. We let it melt. Okay? Is that still water at the end? Yeah. We break it apart. Is it still water at the end? Yeah. Yeah, it is, isn't it? We take a piece of paper, rip it apart. Is it still paper? Yeah. Okay, so those are all physical changes, okay? Other physical changes would be taking sugar and water, sugar and coffee, and we mix them together. It's still sugar, right? Yeah, it's dissolved in the coffee, but it's still sugar. It didn't suddenly become hydrogen peroxide and now I'm going to die drinking that coffee, did it? Okay? So that's still a physical change. Okay? Let's talk about chemical changes then. So this is going to result in the change of identity of that substance. So you're no longer going to have the same substance. You don't have sugar anymore. You don't have water anymore. You don't have that same thing. Okay? It's going to change that chemical compound, the substance. And so that's going to be where a substance undergoes such a change. That's going to be your chemical reactions. The classic example of chemical reactions is burning stuff. Okay? Because it's the one you're most familiar with. If I burn sugar, do I have sugar at the end? No. I just think it tastes really bad, right? Okay. By the way, caramelization is not burning, in case you're curious. That is a different process, making caramels, than burning sugar. If anybody didn't know that. If I can do electrochemistry experiments where I'm going to generate hydrogen and oxygen gas from water, is that water anymore? Do I want to take a drink of that? Hydrogen and oxygen gas, there's not even a liquid, is it? Okay, and it would blow up if I put a spark to it. So, very different, isn't it? I put fuel in my engine for a gas car and it burns. Do I have gasoline coming out? No, it's definitely not gasoline anymore, is it? It's CO2 and water. Okay, if it burns clean. So these are all chemical changes. Okay. So again, chemical changes is going to be where we actually have what's called a reaction that takes place. And so this is going to be a reaction. This is how you write reactions. Okay. It has a shorthand notation. You'll notice it looks a lot like a math problem, doesn't it? This plus this equals that. And maybe that's plus something else, right? Okay. And it is. It's just like that. This yield symbol, that's an equal sign. Okay. That becomes this. And they have to be equal. Okay. Because what do you know about matter? Does it get created? Does it get destroyed? Does it pop out of a closet? No. No. Did you know that's actually the fundamental difference between ancient people and modern people? And people that have not had any education and developed society past a certain point? It's like the most fundamental difference. Ancient people would have opened their closet and they would have full on expected, I might have a piece of gold in there, I might not. I don't know. I could go over there a mile away and a goblin could pop up. Dragon, I don't know. It could happen. Anything. And they believed that anything could pop out at any time. It did not have to have something it was created from. And there was creation and just things came into being. Okay? That was a fundamental belief. And now this thought process that you don't create or destroy anything, right? You just change it. Okay? That's like a fundamental mental concept of modern people. Okay? And it's almost worldwide. You can still find some groups that are very, very isolated. I'm talking, this is not levels of isolation like middle of the rainforest levels of isolation. I'm talking way past that. Because middle of rainforest, they know what TV is. And like they have a loose concept at least. Maybe never seen it. But they know. They have some ideas. But like if you find isolated enough people, they will actually believe like I open my bag, I could have a bar of gold in there. I don't know. Anything could be. And so reactants, these are the reactants right here. They're what you put into the reaction. This right here is your reaction arrow. It's going to be what you're changing. It's telling you I'm changing something and going to this other side. And then this is your products, and that's going to be what you make out of this, okay? And so right here we have carbon, that would be coal. We have it reacting with oxygen. This is really pure coal. Most coals are not just carbon. This is going to react with oxygen. And this is going to give me heat coming off of this. It needs heat to start this reaction actually as well. And then this is my product is CO2, right? Carbon dioxide. Now these symbols down here, these are going to mean solid, gas. Then there's also an L for liquid. And then as you mentioned before, AQ for aqueous. And those are the major phases we're going to worry about in most reactions. Plasma and Bose-Einstein condensate and blah, blah. Other stuff is just not something you're going to encounter. Okay. Plasma is possible to encounter because that actually made it in every lightning strike. But you're not in lightning strikes and you're not doing anything with lightning strikes. So we're not going to really talk about that stuff. Anybody have any questions so far? Now, what has to be true about this chemical reaction here? If I start with one carbon, how many carbons can I end up with? One. I can't have multiple, can I? And wait a second. If I start with one carbon, can I not have a carbon? No, I have to have a carbon, right? I have to have the exact same number of each of these elements, each of these electrons, each of these atoms as I started with. Okay? I can't have any difference because I can move things, I can misplace them. But I cannot actually create or destroy anything, right? That's not the domain of us. Okay? And so, balancing chemical equations. This is actually called the law of conservation of mass. That's actually the scientific law that we're talking about right here and underpins this. We'll talk a bit more about laws and theories after I finish this on the next lecture, probably. So what we do to balance these is we use what are called coefficients. It's the same thing as math. You have 2x, that 2 was a coefficient, right? So we have 2c, or we have a 2O2, okay? And they're multipliers of what we have, right? The compound we have, okay? Keep in mind that this O2 here, that is a different thing than O3, isn't it? That's a different thing than O4. Okay, O4 is explosive, O3 is ozone, O2 is the gas you're breathing right now. Okay, that's the one you're getting oxygen, right? Okay. If I made you breathe ozone, you wouldn't be so happy with me, would you? For the 10 minutes you survive. Okay. And so, if you change this number down here, let's say you needed 3 oxygens for the other side. Can you change that number from 2 to 3? No. You change the compound you have, right? You have an entirely different compound. You're going to go to jail just like I did for poisoning all my friends with H2O2, right? Yeah. It's not good. Not okay. Okay. The difference between carbon monoxide and carbon dioxide. Carbon dioxide you're breathing out right now. Carbon monoxide would suffocate you and kill you. Carbon monoxide, carbon, 1 oxygen. Okay? So literally difference between life and death, right? All right. So you're going to put coefficients instead. You're not going to change those numbers, which are called subscripts. Okay? That's these subscript numbers down here. You're going to put a number in front, like you would for a 2x, 3x, 4x, right? Because you're literally multiplying that compound. You're saying, I have 2 O2 oxygens. I have 2 H2O's waters, right? Okay. Just like a math formula. This is actually the steps for balancing a chemical equation. I put them in there for you guys to look at. Some people get helped by them. I have not found them particularly helpful for the majority of my students, but I do know there's a contingent, okay, that actually finds these very helpful. I won't actually talk about those ever again, and so they'll just be there in my slideshow for you, okay, if they are something that helps you. Same as my intro part where I have like a table of contents, and the same as the study guides at the end that you'll see, okay? They're there for your information. I'm not going to talk about them. It doesn't help you. So math. Let's talk a little bit about math. So for measurements to be easily compared, we have to define a measurement system. This was actually done through the System International Day Units, which is the SI units. This is actually what the modern metric system is based off of loosely. The standard unit for mass is the kilogram. The standard unit for volume is going to be the liter. And the standard unit for length is going to be the meter. Now, what we're going to do in science is we're going to have to use prefixes. Okay? And what prefixes are going to allow us to do is they're going to allow us to make these numbers that these represent smaller or larger by just using the prefix to change that. Okay? You're already seeing a prefix. Kilo. Right? The kilo, kilogram, that's the prefix. That means we have 1,000 grams. Okay? So a kilogram is 1,000 grams. If I want to get paid 100K, then how much do I want to get paid? Nobody knows? 100,000, yeah. Yeah. If nobody knew, I was going to ask for it right now. Everybody give me 1K. Okay. So that was the prefix, isn't it? You've been using the prefix almost your entire life, probably. And you never even realized you've been using kilo. You're asking them for kilo dollars, aren't you? Okay? So you're asking for $1,000 increments. All right? Always been using it, probably didn't realize it. Okay. You've also probably used milliliters before, and milli is another one of these prefixes, right? So right here are the prefixes that you'll need to know for this course. If you have other science courses, they may have a more expanded list depending on the course. This is the important ones because this is more like a nursing chemistry, sort of medical chemistry stuff, okay? And so right here we have giga. You may have heard of a gigabyte or a gigahertz. Okay, that right there is abbreviated capital G. That's why you see that capital GHz for gigahertz. This is actually going to be 1 billion of those. So if you have a gigabyte, you have 1 billion bytes. If you have a gigahertz, you have 1 billion hertz. Okay, if you have a gigadollar, you have a very nice little nest egg. You're doing very well for yourself. Okay, so here we have mega. Mega is going to be capital M. And this one's going to be your internet speeds, right? Usually quoted to you in megabits. Okay? Not megabytes, megabits. And that's because there's 8 bits to a byte. And so they can quote you a much larger number. You'll think it's bytes, and then you'll go, I have a really fast internet speed. Not realizing you have an eighth that speed. Okay. Yeah, they're fun. Telecoms, man. So that is a million. So if you have a megabyte, you have a million bytes, right? A megabit, you have a million bits. Okay. And so megahertz, like the radio stations, million hertz, right? All right, so kilo, this is lowercase k, that's 1,000 of something. So if I have a kilogram, I have 1,000 grams, of course. If I have a kilo dollar, like you always quote your money probably, then I have $1,000, don't I? Okay. This is your base unit. It would not have any prefix. It would just be the unit. So you have a gram, liter, meter, etc. Okay. There's a really funny thing that a bunch of people actually don't know, that there is a unit called gram. It's not common, but I've actually run into a few people, and they think it's kilogram is the unit. Yeah. And yeah, it's not. There's 1,000 grams, and that's kilogram, right? Okay. Deci, everybody knows decimal, right? Okay. Tenth. So this is a tenth. This would be 1/10 of a gram. Okay, decigram. Decimeter, 1/10 of a meter. Okay. Now you can actually turn that around if you want. There are 10 decimeters in a meter. Okay, 10 decimeters gives me a meter, doesn't it? Okay. Centi, like century, right? And so this is the other one of those. Century would be 100 times. Centi would be 100. Okay. And so 1/100th of a meter would be a centimeter. Hey, I've heard of that one before, have not. So 1/100th of a meter, centimeter. Anybody ever heard of cc? Yeah? Yeah? Okay. Anybody know what that is in terms of units? How much volume that is? It is. Yeah. It's the exact same thing as milliliter. And what that actually means is cubic centimeter. So it's a cube that would be a centimeter on each side. Okay. And so stat, give me 10 cc's. Here, 10 milliliters or 10 cubes, that'd be a centimeter on each side, right? Can also be represented by cm to the third power. Okay. Okay, so milliliter, you know that one. 1,000th of a liter, right? And so that's actually 1,000th of a liter right there. Micro, its actual symbol right there is mu. People put that, and sometimes it turns into a U by accident. So whenever you're looking at this, be very careful, especially if you're going to end up being a nurse or something, or a doctor, or if you really, even as a patient, you should be careful about this one, okay? Is that sloppy handwriting can turn this mu symbol right here to an M. Okay? Now, a microliter is 1/1,000,000th of a liter, right? A milliliter is 1,000th of a liter. The difference between these is 1,000 times. Okay? So, my own advisor, and I've talked to literally dozens of people that have come up to me and like, Dr. Clausen, you're absolutely right about this. Somebody did this, and I had to block them from doing this. Okay, I taught this class for nurses. I've taught, I guess, about 1,000 something nurses. And I get people coming up to me in like the middle of Walmart. They're like, Dr. Clausen, you're right. Somebody did it. Tried to do it. And I blocked them. And what happens a lot in like very busy hospitals and medical environments is the doctors write very sloppy and very fast, right? And so the nurse then would go off with the chart, and the doctor wrote microliter. Okay? And very sloppy, very quick. If you write that, really sloppy, very quick. What does it look like? Him, right? And so the nurse then gets over to the IV machine that you can then dial in this quantity. And some IV machines will block this, but some don't. Okay, because they can be used for a multitude of different things, right? Sometimes you do need a milliliter or milliliters. Sometimes you don't. Unfortunately, they tend to do this a lot, and it causes issues where they're doing things like morphine. And so this happens a lot where the nurse will go up to the morphine machine, click, 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 beep, 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 beep. Here I go, unlock it. Let me get my key. And then if you don't stop them, they'll unlock the damn thing and put you into milliliters of morphine per minute. Okay? Which is a few hundred times past what you could actually take as a human being. Okay? You will die and you'll be very, very dead. And you will not be able to block it or realize that you're dying because you will be stoned out of your damn mind. Okay? You won't know anything is happening or care anything's happening. You're going to slide off into death real peaceful, but you will definitely be dead. Okay? Now, I have had dozens of people go, Dr. Clausen, you're exactly right. And in fact, my own scientific advisor, he has a story where he was in the hospital and his nurse tried to put the instrument up and she was reaching for the key. That was actually a real story. That my scientific advisor stopped his nurse from doing that because he's like, wait a second, let me see that damn chart. That looks like a micro. I said, go back to your fucking doctor. No, he really did. He would yell at you and tell you he's gonna take you out back and shoot you. He was a wild guy. But no, she fought him and told him he doesn't know what the hell he's talking about. And was like, I'm gonna put your morphine up. I don't care what you say. And he ripped the tubes out of his arm, threw them on the ground, and said, no, you're getting your damn doctor. And he was right. Like, it's a very, very, very common mistake, and people overdose people all the time, and unfortunately, a number of those turn into deaths. Okay, it's a pretty common malpractice. In medical, they typically put MC to try to avoid that. Okay? Unfortunately, I don't think it actually helps as much because the C is super sloppy, right? So let's say you do this very sloppy. What does that look like? Still looks like him. I don't know what to tell you there. Check your charts. Yeah. If you're the patient, still, they start trying to put you at huge doses. If they hit that little dial more than about 10 times, you should probably go, wait a second. Wait a second there. That seems like a lot. Okay. Nano. You guys probably have heard of microbiology, right? Okay, that's measured in micrometers. And that's where you would have heard that from. Or microchip. Nano. Nano processor is the thing I can think of, or nano drop that you might have heard of. So both of those, anyways, are this nano, and that is 1/1000th of that. Okay? So, for example, there would be 1,000,000,000 nanometers in a meter. Okay? And so a nano chip is measured on those scales. A nano drop would be 1/10000000th of a drop. Okay? Very, very tiny amount. Okay, so equivalent units. Quantities that can be related to each other by an equal sign are going to be what's called equivalent units. So, for example, 1 deciliter equals 0.1 liter, and that is 1/10 of a liter, right? And is everybody aware of that? Okay, so if we look at this right here, are those the same number? Okay. I've had to start doing this stuff because I've actually run into 6 people that Did not know that. Okay. And so I've had to start being really careful that even like super basic middle school level assumptions, I cannot make anymore. So if you see something, you're like, I don't know this, please don't be embarrassed because education system has gotten unreliable. Okay. So these are what's called equivalents. Those are equivalent numbers, right? And by saying 1 deciliter, 1/10 of a liter, right? I'm saying 0.1 liter, aren't I? They're the exact same thing. So that's equivalence. These can be turned into what are called conversion factors. Okay? And then they can be used to convert from one unit to another. We can use those to convert our different prefixes. Okay? And so, for example, whenever you're doing math, both sides of the equation, you can always multiply by 1, can't you? Okay? Anything that would sum up to 1, you can always multiply both sides. Well, this right here is literally saying multiply by 1, isn't it? Because this is the same thing as this. Okay? And so whenever you do conversions, what you're going to do is you're going to use something that you know to be true that are the same things. Okay? And essentially what you're doing in a conversion of units is just multiplying by 1 over and over and over in fancy ways. Okay? You're going to be multiplying equivalencies across the thing, right? And it'll convert your units for you. Okay? So whenever you're doing this is how you get a conversion factor. They're always going to be something that the top and bottom are the same thing. They're equal. And so they are the same amount. Okay? And that's a conversion factor. And this means the same thing either way, doesn't it? They're the same amount. Okay? And so you can say 10 deciliters divided by 1 liter, and that would be, well, they're equal on both sides, so it's just 1. Okay? Or 1 liter is 10 deciliters, right? Now, these are going to allow you to do some nice math tricks where you can convert a quantity from one unit to equivalent quantity in a different unit. And so you can start doing things like 3.33 feet equals 1/3 of a meter. Okay? So 10 feet is equal to 1 meter. Okay? 1 meter would be 3.33 feet. Repeating. Okay, so this right here are different steps. This is typically called dimensional analysis. There's a few different names you can call this. It's honestly doesn't matter that much, but dimensional analysis is a very common way. So let's talk about significant figures. You've all probably encountered these before. You may not have realized it though. So when we measure matter, this can rely on the precision of our instruments that we use to measure it. It's going to be very important to report these calculated answers reasonably so that we're not putting a bunch of different digits that makes it seem like we're extremely precise or extremely imprecise. Okay? And so when reading a measurement from a non-digital device, there's some level of uncertainty in our measurement. In any measurement, the significant figures are going to be digits where we know with certainty plus 1 estimated digit. So you always estimate 1 more digit in a scientific measurement. Okay? The best way for you to understand significant figures is, do you know your bank account right now without looking down to the penny? Or even fraction of the penny? Your bank account's actually in fractions of pennies, isn't it? They don't report it to you, but it is. So, what do you usually tell people if you had to? My bank account has like $1,000 in it, right? Okay? And that's your degree of certainty. You know you have 1,000. Your next digit, you're not so sure, right? And so you might say, I have like $1,500. Okay? You could have 1,300, right? Or you could have 1,490. Or you could have 1,570. But you don't remember those other digits, so you don't know. You're not certain. Okay? And that's what we're representing here. We're representing how certain am I in my measurement. If I were to use this to measure things out, well, I know this is about 24 ounces. So I know it's multiples of 24 ounces. Okay? I can't tell you I'm going to measure out to a half an ounce, can I? I don't know that. I'm not measuring that degree of accuracy. And so I'm not going to report that, am I? Okay. But if you do the work and you got that degree of certainty, if I sat there and I took a balance and I perfectly measured out this quantity, I'm going to report those decimal places because that's a different level of care and a different level of precision, isn't it? Okay. And so that is going to be what significant figures tells you. Now, digital devices are very nice in labs and chemistry because they're going to actually give you your number of significant figures on that digital readout. So whenever you read a digital device, you should just write down what it says. Okay, that's all you need to do. Write down what it says. Those are the significant figures. That's it. Okay. If you measure with a ruler, for example, so I have my ruler, right? Okay. And I'm sitting there measuring, right? So it ends right here. Okay. So I'm measuring. I'm not to 1, am I? Okay. Am I half? Not quite. And I can tell I'm not half, can I? I can very successfully tell. But what am I? Yeah, 0.3, 0.4, something like that, right? And so that's my last digit of certainty is the 0, right? And then I have my one uncertain figure, which is going to be the 0.3. Okay? And so that would be the sort of value I'd report there. I'd report I'm 0.3, 0.4. One of the two, right? I'd report a value like that. Would I report 0.352? I don't know that. No way I can tell that, right? Doesn't make any sense. That's way overestimating my ability to tell what that is. Okay? So let's talk about some of the rules you need for significant figures to understand them. So zeros tend to be troublemakers in significant figures because their significant is going to depend. It's going to depend on the position in the number. And that's because we use zeros in our numeral system to represent where it is in terms of tens, hundreds, thousands, right? Can I write that number like this? No, it's wrong, right? It's not 100 anymore. So I needed those zeros, even though they may not be significant, right? I still have to put them because they're placeholders, okay? They're telling me my place. So if a number, zero in a number without a decimal point is significant, that can be shown by putting a decimal point after that 0. So if I wanted these to be significant, they're not significant right now, I need to put a decimal place. Okay? That makes those significant. All right? If to indicate a significant 0 in large numbers, you would draw a line above the significant 0. So let's say I wanted 1,000. These are significant. I would do this. Okay? The last one here, the 0, this one's not significant. Okay? And so I only know my bank account is 1,000. I don't know the dollar amount at the end. Okay? I don't know if I have $1, $5, $3, whatever. Don't care. Okay? Didn't keep track. May have bought a burrito. I don't know. All right. Let's talk about exact numbers. So exact numbers is going to be numbers that are used in defined systems where we have a conversion factor is the most common place to find these. And they're going to be counted items are also the most common place to find these. And they're going to have an infinite number of significant figures. They don't have the concept of significant figures because they are exact. Okay? So the number of students in this room, if I was to count those out, would I get a 0.1 student? No, because you're people, right? Your number of objects that I can count. Okay? If it's so many people that I can't count everybody, I might get fractions, right? And then I might not have a certainty anymore. Like the population in the United States, we don't know the thousands. Like how many thousands of people there are. We know the millions. We know that mostly. So those would be exact numbers. Exact numbers would be things like conversion factors are oftentimes exact numbers because we have set the units to be that way. Okay? So for example, there is 100 centimeters in a meter because we have set that to be that way. There can never be anything different because if a meter changes, so does the centimeter change, right? Feet are like that now. There's a bunch of different systems that are like that. They are all set to be the exact amounts, okay? So this is some different examples. These are non-zeros. So if we look at this, this has 1, 2 significant figures because it has 2 non-zero numbers, right? And so that's 2 significant figures. This one right here has 1, 2, 3 significant figures because it has 3 non-zero numbers in it. And so that's 3 sig figs. Okay. Let's look at zeros between the numbers. So 101, the zeros between, and so that has to be significant. If this is significant over here, the 1, that 0 also has to be. Okay. And so that would be 3 significant figures. That's 3 digits, 3 significant figures. This right here is going to be 1, 2, 3, 4. There's 4 digits in it. That's 4 significant figures. Again, that 0 right there has to be significant if the number on the other side of it is. If that wasn't significant, then I didn't need any of these numbers down here, right? Like if I don't know how many thousands of dollars I have in my account, does it matter how many pennies I have? No. So if you lose significance, if you're uncertain, then everything after it doesn't matter, right? Yeah. Those are uncertain as well. So a 0 at the end of the number, this right here has a period, and so that is significant, right? The period makes it significant. This one right here has a decimal place. That makes all the zeros after that decimal place significant. Okay? So when you're looking at something with a decimal place, you start at the left and you go. As soon as you have a non-zero number on the left, all the zeros become significant. Okay? As soon as it has a non-zero number on both sides, it has to be significant. Okay? Let's look at some other examples. This one right here, see these zeros in front? Not significant. They're just placeholders, aren't they? This right here would be the first significant digit. If we had more zeros after it, that would be significant. Okay? And so that's 1 sig fig. This one's 2 sig figs because that's the first non-zero, isn't it? This one right here doesn't have any decimal places, no lines above it. And so these are not significant digits right here, the zeros. They're just placeholders. Okay? So if you don't have any line above it, no period, that's going to tell you that, well, you start on the right and you work your way left. And the first non-zero digit, that's going to be where your significant figures start. Okay? And so 2 significant figures. This one has 1, 2, 3 significant figures. Again, no period, no line above it. So these zeros are not significant. Okay, so whenever we calculate numbers and we do rounding, how do we round? Let's say we have a 6 after our number and we need to round. What do? Round up. What about 4? Down. What do we do for 5? It fell apart. So 5 is actually the exact center of our digits, isn't it? Mm-hmm. Oh, is it? Yes, it's just finished. Yeah. Let's go ahead and wrap up. Go ahead and go. You all have a wonderful day. Yeah. And I'll start on this next time. You can figure out, think about it. You'll have dreams at night all weekend. What do I do when I round 5? You've been taught wrong, in case you want to know. Take care now.